of our Today, I'm going to talk about some of our recent research on building reliable and robust model explanations, what that means, how do we think about it, and so on. So the way I'll try to do it, just so that like for people who are also new, they can get a slight context, is that I'll try to spend the first few minutes just giving a little bit of context about what are some of the popular explanation techniques, and then start discussing the problems that they have that have been highlighted by our own prior work as well as prior work by some other amazing researchers as well. And then I'll get into the exact methods that we propose in order to mitigate some of the issues that I'm touching upon. Okay, so with that said, let's get started. So as we all know by now, all the participants who are here, machine learning is becoming increasingly popular or increasingly being deployed, or at least considered for deployment in domains that are critical, like for example healthcare and law and finance and so on, where it's important to make decisions correctly. Otherwise, human lives can be impacted, a lot of money can be impacted, health can be impacted, and so on, right? So these kinds of high stakes decisions, we need to get it right, and machine learning models are increasingly being used to assist human decision makers in these kinds of decision making, right? And given that those are the settings that we are increasingly moving into, as a field, where there is a doctor and potentially a machine learning model, and together they decide, for example, what treatment to recommend, what diagnosis to give. In such settings, interpretability becomes key, right? So the doctor, or the judge, or any other decision maker should roughly be able to get some sense of what features or what aspects is the model basing its decisions or predictions on, and if those are, in fact, like valid features, good features to use when making those decisions, right? So some form of insight into like what exactly the model is doing and how it is doing it would be very helpful for decision makers in thinking about how much to account for the model predictions when making their own decisions, right? So just a high level overview of like what has been the rough approach to interpretability in machine learning. I'm sure several of us would agree that there are some simpler classes of models that are somewhat more easier to understand. Again, assuming that these are also like shallow models, or like, models with smaller complexity, like a shallow decision tree, or like, a logistic regression or a linear regression with fewer features that are being used and so on. So such simpler classes of models are often easier to interpret, at least in terms of feature importances or what features are being used predominantly when making predictions, right? But as we all have seen, this whole mega revolution of deep learning, it has clearly demonstrated that complex models can achieve comparatively higher performance, especially in certain settings where there is high dimensional data. So it has become more commonplace to use models like deep neural nets, random forests, and so on, right? So what is the solution? So given that there seems to be this sort of tension between, should I go for a complex model that is more accurate, or should I go for a simple model and like lose some bit of accuracy? Given that tension, one solution that has emerged within the field is that build your complex models that are accurate and then explain them in a post hoc fashion using simpler models, right? So build whatever accurate model you want, however complex it might be, and then we'll use this post hoc probing tools to try and explain how that model might be making individual predictions, for instance, right? And these classes of techniques are broadly known as post hoc explanation techniques. Okay, so the agenda for today is that I'll give a brief intro and highlight the challenges of existing post hoc explanation techniques. I'll then present some of our recent work, which proposes an approach that mitigates, or at least tries to mitigate, some of these challenges, and then we'll have a summary and conclusions. All right. So first, let's start with the post hoc explanation techniques, right? So I already just kind of gave a very high level intro to why post hoc explanation techniques became popular. So what are these kinds of techniques? So typically, a lot of these techniques consider a complex model as a black box. Let's say there is a complex neural network that we want to try and explain. A lot of these methods require very minimal access to the internals of that model, right? So a bunch of the methods that that we have today actually just need query access. They should be able to just throw a data point at this model and get a prediction. They don't really need to know what is going on inside the black box, right? And there are of course a few other approaches which require gradient access, but nothing more than that. So roughly, with little to no access to internal details of the models, these explanation techniques are trying to explain the behavior of the black box models. And there have been several types of post hoc explanation techniques, like local versus global explanations has been one major bifurcation. Local means the focus is on explaining individual predictions, and global typically means the focus is on explaining the entire behavior of the model, right? And then depending on the exact techniques being used, there have been other classifications like gradient based versus perturbation based methods, and so on. So this talk and today we'll be talking a lot about perturbation based methods, and I'll say what it is in a little bit. You'll get clarity on that. Okay. All right. So, and examples of some popular post hoc explanation techniques include LIME, SHAP, Anchor, Muse, gradient times input, integrated gradients, and many, many more, right? So I have kind of highlighted LIME and SHAP here because these are the two approaches that we'll be focusing on as part of today's talk and delving more into their details, right? Okay, so let me start with a very high level overview of like what Lime and Shap do. We'll be mostly focusing on Lime, and a lot of the things that we discussed today are also applicable to several variants of Shap. Okay, right. So both these approaches are actually model agnostic in the sense that the underlying model that we are trying to explain can be anything. All they need is query access. Like they need to be able to send input to the model and get a prediction, right? So potentially probability of being classified as a particular class, right? And they focus mostly on providing local explanations. That is, their goal is to explain individual predictions of any classifier by learning an interpretable model locally around each prediction. And we'll go a little bit into depth as to how they do it, but their primary emphasis is on local explanations. Of course, there are also solutions proposed in these papers and others as to how you can construct global explanations by picking some subset of local explanations. But we are mostly going to focus on local explanations in today's talk. Okay. Now, what do they output? They actually output feature importances or feature attributions for individual instances, right? So these basically tell us how important each feature is to the prediction that the model is making, or how much is the model using each of these features in that individual prediction that it is making, right? Because we are focusing on local explanations, which is about explaining the rationale behind individual predictions. Okay. So how is Lime doing all this, and like what is its underlying intuition, right? The intuition that Lime exploits is that while complex models might have complex decision surfaces and are harder to understand globally. For example, in this picture, you see this kind of a blue shaded region and then like, a light pink shaded region. So those could be thought of as the two classes according to the classifier, right? So if you see, the decision boundaries are highly nonlinear, right? So while it might be hard to explain those at a global level, they might appear very nonlinear. If you zoom in into little pockets of this complex decision surface, these models will start behaving linearly. So that is the intuition that these approaches are capturing. For example, if I zoom in close to this like red plus mark that you see, that instance, the model is behaving like a linear model in that particular local region or that particular local pocket, right? So using this intuition, approaches like Lime then try to fit local linear models to approximate the local behavior of this underlying complex model, and then use that as the explanation, right? So that is the basic insight. And how do they do this? Let's again say that we are trying to explain the prediction of this plus red point that you see here, which is highlighted boldly. The way you try to explain the underlying model's prediction of this point is the following. Take that point, perturb it a bit, and basically create a bunch of instances around it. So that can be thought of as the neighborhood or the local neighborhood around that instance, right? And now we can take that and then fit like a linear regression model which predicts the probabilities output by the underlying, let's say a deep learning model. And this linear local model will essentially capture the local behavior of the underlying, let's say a complex model like a deep learning model, right? So take a point, perturb it, create a whole neighborhood, and fit a linear regression there, which maps the instances to the probabilities. So that is their simple solution, right? And how do you do the perturbations? There are, of course, different ways. If the features are continuous, you can take a point, add some Gaussian noise, and then generate neighborhood. But what is kind of proposed in the Lime paper is that, they think of all features as like binary features, or at least they can binarize them. And what they do is, out of all and each feature has a value of 0 or 1, and out of all the features that have a value of 1, for a given data point, you randomly pick a subset of features and then flip their values to 0, right? That's how they're creating the perturbation. So you have a vector of ones and zeros, that's your feature vector. Take that vector, there are some ones in this vector, obviously, pick a random sample of some features which have ones and flip those to zeros, and they're calling that a perturbation, right? We'll come to this as to if this is a good way to do this perturbing or not, but that is what is being like at least discussed in the paper. Of course, there are other perturbation strategies that have also been proposed, right? But this is at a high level what Lime is trying to do. So what then does this output, right? If you look at the top piece of the slide here, you almost see that it is outputting point-wise feature importances. So let's say like the x-axis is this absolute feature importance, and on the y-axis you see different features, right? Like for example, misdemeanor charge. You can see that misdemeanor charge has like a feature importance of like 0.23 or something, and green is positive contribution. So this has plus 0.23, and priors has like a feature importance of somewhere around like 0.18, 0.19. And then this female has a negative contribution, which means its feature importance is minus 0.12. So yeah, these are just kind of giving point-wise estimates of feature importance if we are thinking about like a tabular data and its features, right? In case of images, what it is doing is, or how they tackle images is that they basically take an image, split it into several super pixels, which can be obtained by taking the intermediate representations of like very large nets like Inception Net or something. You take their intermediate representations, take the pieces of the image that you get as super pixels, and those would become the features, right? And their feature vector would be 1 or 0. Is the super pixel present in the image or not, right? After doing that, the output that they get, for example, in this case, is highlighting the top 3 important features. You can see the face of the dog, and then the electric guitar strings, and so on, right? So that those are the important features that Lime recognizes. So these are the explanations that Lime outputs, okay? Just to give a high level idea about the formulation, because we'll be talking about this in the context of the new approach I'll discuss later on. The formulation is rather simple, like a typical classification loss. Something similar to that is what you see here. So there are two terms in the formulation of Lime. One is the loss function, and the other is the complexity function, right? So the complexity function could be something like number of non-zero weights in the linear model explanation, and you want to minimize that because fewer the number of non-zero weights, fewer the features it is using, and it's easier to understand, right? Sparsity is helpful for interpretability. Now, if you look at the loss function on the left-hand side, that is essentially doing this kind of a squared error loss. So you are just trying to match the predictions output by this local linear model, which will be our explanation, and the predictions output by the underlying black box that you're trying to explain, right? G is the explanation, F is the underlying model. So you're trying to make sure that F and G's predictions match on the perturbations that you have generated, as we have just discussed. And we are weighting this using this kind of a distance function, so that points that are closer to the instance are getting more higher weightage than points that are farther away, right? So if points are farther away, then maybe they're not present in the local neighborhood, and we don't care about this model exactly fitting on them, and we can downweight that. So that's roughly the intuition that this is trying to capture, this formulation is trying to capture. Okay, Now, what are like we talked about Lime and all its like internal details and intuitions. Now, what may be some challenges associated with Lime, right? So, the first question we may ask when we see any explanation, and of course, Lime explanations, is that is this explanation faithfully capturing the behavior of the underlying model, right? So, what stops somebody from giving me a junk explanation and saying, look, here is a local explanation, this is what the model is doing? Okay, how to evaluate that, how to ascertain that, right? Again, there are several strategies that have been looked at. All of them have their own pros and cons and their fair share of limitations. For example, one popular strategy is compute weighted r square on the generated perturbations, right? So line, basically we have fit a local linear model on a perturbation set or on a local neighborhood. Now just compute weighted r square, where again the weights are based on the distance from the original instance. So do that, and the higher the r square value, the better the fit, the local explanation is, and the more faithful it is, right? So that is one way that people have been evaluating. But there are some problems with this, which is that this is making the evaluation process dependent on the perturbation set itself, right? So the same thing that Lime is generating, you are basically believing that that is what the local neighborhood is, and you're just evaluating on that. What if that is not a good capture of the local neighborhood, right? So then your weighted r square does not really mean anything if your perturbation set is not a good capture of the local neighborhood. So clearly this is not a reliable measure, and in spite of several metrics that try to use some ground truth, some synthetic models and so on, there is like still like some discomfort among the researchers in explainability, because if you give me a model that I know nothing about, you know nothing about, we don't have a synthetic model that we have a ground truth for, there are no easy and like foolproof ways to say, okay, this is a metric that basically solves our problem and tells us how accurate this explanation is, right? Of course, there are several metrics being proposed and people are still trying to sift through, but this has been an active area of research. Okay. The second thing is stability, or rather lack of stability, right? So what people have actually observed is that small changes to input instances can cause drastic changes in the explanations produced by perturbation based methods like Lime or SHAP. Okay. So in fact, there has been some work which computed this local Lipschitz constant. What they're trying to do is basically just see f here corresponds to the explanation itself. So they're trying to compare relative to the change in an instance. If you make a small change in an instance, how drastically does the explanation change, right? And the higher this value, higher the instability, and the more unstable the explanation method is, and it's bad. Okay. So if you see this particular picture, what you see is that like Lime and SHAP have like quite high Lipschitz estimate compared to even some of the other approaches. But like Lime and SHAP basically have higher values on this metric of local Lipschitz measure, indicating that they're rather unstable. Okay. All right. Then, in some of our recent work, we have noticed that the problem does not just stay with stability. In fact, the problem runs even more deeper. So, there is a lack of consistency in the explanations produced by Lime. What do I mean by that? If you take Lime and basically run it repeatedly multiple times, don't change anything, no hyperparameter changes, nothing. Take a point, keep running Lime in the same way multiple times, what you see is you actually get different explanations each time you do the rerun, right? And if you look at, let's pick the last two figures. In this case, there was an underlying nonlinear model. You see this kind of contour surface of that, and then for that we were basically on such a model, to explain such a model and a particular instance there, we were basically running rhyme repeatedly, and what you see is this entire blue region is the path or the region that it traces. So you get multiple, each line there is an explanation, but you can get like a whole range of explanations, which is shown by that blue region, right? So which means it's problematic because you don't know then what explanation to finally give to somebody, or like what to rely on, right? And what we observe is that here this band is actually wider when the number of perturbations is fewer. That is 25 perturbations, this like, the range of explanations being generated is much larger, whereas with 250 the band already kind of condenses a bit, right? uh, so that's one observation. But what does that imply? uh, Is this a problem with having too few perturbations? Can we resolve this problem by like just, increasing the number of perturbations? And another problem is we don't really even know what is the optimal number of perturbations. Like when I run my lime method with like, let's say 100 perturbations on an instance, is that too less or is it too much, right? I have no clue. Like there is no way to know for me, right? Just to be safer, can we really run this on like say 10,000, 20,000 million perturbations, just to be safer that I'm getting the band as narrow as possible and maybe I'm just hitting that one true thing? Is that possible? Is that a potential solution? That also has its difficulties because it's not exactly computationally easy to do that, right? So and one of the main reasons is that querying complex models repeatedly for labels can be prohibitively expensive, when you think about the time it takes, right? The clock time it takes. And larger number of perturbations, sure, you can tell me like run it on a million perturbations and you'll solve your problems. But large number of perturbations means large number of model queries, which makes this process much more challenging to even generate a single explanation. Forget explanations for the entire data set, right? So yeah, that means actually generating reliable explanations using lime can be very, very computationally expensive. Okay, and this is not a viable solution to just say run it with a million perturbations. All right. So, with that groundwork laid out, now how do we address some of these problems? We talked about not knowing how to even understand if an explanation is good or not, right? So, if somebody gives you an explanation and gives you a weighted R square, for example, for Lime explanation, can we still trust this? Maybe not, right? Because the perturbation set can determine what this weighted R square would look like. So we have a problem with knowing if an explanation is even good enough to be trusted. We have a problem with stability, consistency, scalability. So there are a bunch of challenges there. And in this recent work that we have, we are trying to provide like a first cut solution to these problems. Okay. What let me first show you what we are trying to do in terms of our explanation look and feel, and then I'll talk about like how we are trying to get to that, right? So if you remember, this is the Lime explanation that I showed few slides back. Here is like an explanation that we got for an instance on the Compass data set with 100 perturbations using Lime. And here is an explanation for the same instance with 2000 perturbations. What you see is each time Lime will give us a point estimate of the feature importance of each feature. But for the same instance, you can see that depending on the number of perturbations, these have changed. Like for example, here it is the importance of this is plus 0.23, but here the importance of this is like minus 0.21, right? So just kind of that has also given me different explanations. Now this is confusing. So instead of relying on point estimates of feature importances, what about if we think of these as distributions, right? For example, here is what our method outputs. Of course, there is a mean feature importance, but along with that, there is also this kind of a distribution that tells about the uncertainty associated with this feature importance estimate, right? So what is the range of values that can be taken by this particular feature importance? That is how it is thinking about it, as opposed to just thinking of it as point estimates. Now, if you see what this is showing is with 100 perturbations, this uncertainty is much higher. You see this distribution being like much spread over a much broader area, whereas with 2000 perturbations, this is much narrower, right? So we are getting more and more confident, right? But if you see, these estimates are not wrong anymore. So this is still lying within this zone. It's just that the final estimate is like tending to somewhere here, right? So as opposed to just giving point wise estimates, if we give this distribution, we can give a more accurate picture to the end users as to like what your feature importances are, right? And at what confidence level. So that's what we are trying to do. And how do we do that? By taking the Bayesian route. And what we try to do is we construct a Bayesian locally weighted regression that can accommodate the Lime and Sharp weighting schemes, right? So here is what the generative process roughly looks like. This is a Y is the black box prediction. So Y is modeled to be a function of phi transpose Z. y for the prediction for a particular z being one of the perturbations, right? So the black box predictions y for one of the perturbations z is modeled as a function of this product, which is the product of the feature importances multiplied by the perturbation instance itself, plus this error metric, or like this error function, which is actually distributed as a normal distribution with a zero mean and this variance. Okay, this variance, what is its significance? This variance is basically bringing the line weighting function or the distance function, where again we can think of this as the cosine distance between the perturbation z and the original instance x. So the higher the perturbation, so the higher this distance or the higher the value of this function, the more there can be scope for error, because the farther the point is, the more it is likely to not be in the local neighborhood, and it is not really our job to model that particular prediction, right? So that's how you think about it. And then of course this is the prior on this. The feature importance has again a prior, which is a normal distribution, and this psi square, which sorry, sigma square, which appears both here as well as here in the variance terms of both the error as well as the feature importances, that is modeled as an inverse chi-square distribution. And we try to keep the priors here as uninformative as possible so that we can learn more from the data. Of course, if you have a domain where you know priors about the model and the behavior, then obviously you can set these priors. But for now, we are trying to set the priors as uninformatively as possible, right? So these two are, of course, the priors. Now, given the priors and given the generative model that you saw, the conjugacy, because of the conjugacy, you get the posteriors to be these kinds of functions. So the sigma squares posterior distribution would be like a scaled inverse chi-squared function with these parameters. And then this phi, which is the feature importances, a posterior distribution would be normal with a mean of phi and this parameter as the variance, right? And in fact, what we see, or at least the way we have formulated this model, is such that we can compute all the parameters required in closed form. For example, this phi transpose, we can compute it using a closed form expression, and even v phi and so on. So if you see, this phi transpose is the mean feature importance, right? And the mean feature importance of our, the Bayesian phi parameter that we have, that actually turns out to be the same as what we use to estimate feature importances in Lyman Sharp. Okay, so our mean is the same, but we are also able to estimate this whole uncertainty distribution around it. Okay, but it does not stop there. There's more. So our model captures two kinds of uncertainty. One is the uncertainty on the feature importances itself. And how do we get that? How do we get this uncertainty distribution? We compute the posterior mean using this closed form solution. And once we have this mean of the feature importance computed, we can then just plug that into this equation and repeatedly sample from this distribution and then get like a credible interval, right? Like a 95% credible interval. So that will give us the distribution, right? So you take this closed form value, plug it in here, and then just sample repeatedly from that distribution. That will give you what your 95% credible interval would look like for the feature importance uncertainty. And for the error uncertainty, this captures how well our explanation models the local decision surface of the underlying black box. So this is in some sense a proxy for the explanation quality itself, right? If the probability of that error term, we have to measure what is the probability of that error epsilon tending to zero, and that will tell us what is the probability that our local linear explanation that we have is like a perfect fit for the underlying decision surface. Okay, and that we can again get this kind of a distribution for this, like a marginal distribution on epsilon, and then we can use this to estimate the probability of epsilon being zero and get that value, right? Okay. So another important piece with this is this kind of an approach, or the way we have sort of uh, put this or formulated this approach. Users can actually ask questions like these. For example, an end user can say, I need an explanation where the true feature importance lies within plus or minus zero point 0.5 of the estimated values with 95% confidence, right? So what we are saying is, I want this feature importance interval width to be plus or minus zero point 0.5 with 95% confidence. Give me an explanation that satisfies this criteria. And in order to sort of do this or enable generation of explanations like this, we also have some theoretical results which basically help us compute the required number of perturbations to use with lime, which will help us get to explanations with these guarantees, right? So we take these guarantees, user provided inputs plus or minus zero point 0.5 interval width of feature importances, 95% confidence that feature importance lies within that. Then we compute using this theoretical result the number of perturbations that is needed to exactly reach that level of confidence, right? So that is pretty interesting because now we can start getting explanations with guarantees. Okay. All right. Then, apart from all this, we also try to come up with a focus sampling procedure where now now the perturbations in Lime are basically randomly sampled, right? You take a point and then you add random noise, you get some perturbations around it. Now we were like, what if we were to make this more efficient? In such case, what we could do is we could sample perturbations in such a way that we are only querying the black box, or we are only taking those perturbations seriously to query the black box for the ones, or which are the ones that the learning algorithm or your Lime algorithm is most uncertain about, right? So you will basically, instead of randomly sampling, of course at the first iteration you still randomly sample and then you learn a Lime explanation. Then using this you actually know which perturbations this explanation learned is most uncertain about. Now you can only sample, or rather you can sample perturbations and only query the model for labels of those perturbations on which it is most uncertain about, right? So this is the typical uncertainty sampling used in active learning that we are using here in order to improve the efficiency of generating explanations. Okay. All right, so I'll just briefly walk through a couple of quick results and then I'll close this talk. So in order to kind of determine how good these estimates are, we try to do a bunch of things. So one is first to evaluate the quality of the uncertainty estimates. One of the experiments that we do is we take true feature importances of a given model by running Lime and SHAP for a very large number of perturbations. We actually did 20K for some of these data sets, and in other data sets, we had to run it for 1 million to be sure that this is exactly the single explanation that it is outputting every time. But we took that computational pain and then we said, let's run it for a very large number. Whatever we get then would be our true feature importance. And now what we compute is we compute what fraction of the true feature importances fall within our 95% credible intervals, right? So we basically say, let us first generate our 95% credible interval. Now we will see what fraction of the times the true feature importances fall into this interval. And the closer it is to 95, the more well calibrated our uncertainty estimates are, right? And as you can see, in this case, a lot of them are quite close to 95. I think in this case, barring this one, which is slightly lower, or these two, or a few which are slightly lower, they're roughly well calibrated, but maybe probably not as well calibrated as this, right? But yeah, closer to 95 is better, and we are like roughly hitting that zone. Okay. The second thing is we also wanted to get a sense of if our estimates of the correctness of the number of if our estimates of the number of perturbations is actually right. And for that, what we do is we set a desired width of the credible interval and also the level of confidence we need. For example, we say a desired width of, like, say 5 e minus 3, and then with a confidence level of 95%. So if we set that, then we go and observe what actually happens empirically. And in some sense, what this line should look like is exactly like this, because that means whatever you have set as the desired confidence interval width, that is what you are observing in practice after running our method, right? So here we set this as desired, and roughly you can see that here we are observing like 5 e minus 3 here as well, right? That shows us that our observed credible interval widths are kind of calibrated well with the desired credible interval widths that we actually wanted or we desired. Okay. Okay, so the next one is we also checked for the stability of the explanations. And here, what we did is we just computed the percentage improvement over Lime and Shap with respect to this estimate of the local Lipschitz constant, which determines how much is the explanation changing given a small change to an instance, right? And what we see here is in Bayes Lime, we observe quite a bit of like increase in stability compared to Lime across all the four data sets: MNIST, ImageNet, German, and Compass. In the case of Bayes Shap, in one case, there is like a little bit of a dip that we are still trying to probe. And in a lot of other cases, of course, there is a huge improvement in terms of stability. So we have also tried to address that problem to some degree. Right. And the last thing is we carried out a user study where we basically showed people images like this and then mask those images. So basically people will be given some masked images. I'll just talk a little bit about how that masking is done, and we ask them to recognize the exact digit behind that masked image. Okay, so that is the experiment. And what is this trying to tell us? Our goal here is to understand, our baseline explanations better than Lime explanations? And how do we do this masking? We try to mask, or we mask most important features selected by Bayes, Lime, and Lime. So in two different, of course, there's a randomized study, so people only either see Bayes, Lime, or Lime. So we mask the most important features selected by our approach, Bayes, Lime, and of course the standard Lime. And then we mask those features or remove those features from the image. And then we ask people, okay, now can you guess the number, right? Our hypothesis is that the better the explanation, the more difficult for users it should be to get it right when the corresponding top features are masked, right? So, in order for this to work, we actually made sure that our underlying model is very accurate and it is using meaningful features that it's supposed to use in order to make its predictions. Okay, so we tested that. And then our hypothesis after that was that the better the explanation, if we remove the top features given by that explanation from the image, the harder it should be for somebody to recognize what that digit is. Okay, so the user error rate was 25.7% for Lime and 30.7% for Bayes Lime, indicating that if we remove the features that our method flags as important, then it is more difficult for users to really recognize what's the digit in the image. Okay, so yeah, thereby saying that these explanations could be more informative than the Lime explanations. Okay, so with that, we are pretty much at the end of our talk. And, this is one of the initial first cut solutions to address several problems in one shot associated with popular explanation techniques like Lime and Shap. The problems being fidelity, stability, consistency, scalability issues. And to address these, we propose a novel Bayesian formulation for capturing the uncertainty associated with local explanations. And we then leverage these estimates to compute the number of perturbations required to generate explanations that satisfy user specified levels of certainty and also generate them in an efficient manner, right? And I think this is like at this point, the point at which the field is in, it is becoming very critical to continue thinking about how to assess the goodness of a given explanation and also how to find ways and means to improve the reliability of explanation. With that, I would like to close and thank you so much for your time.